your foldable on volumes, solids with known cross sections. This should be on page 139 of your notebook. We're only going to do the first 2 pages today, and we'll worry about the last one on another day. So first of all, you watched some Khan Academy videos yesterday and should have at least a vague understanding of what we're actually trying to do. With the volumes, we basically have a 3-dimensional object. The base region is going to be what is in your XY plane, the bounded region that you have in your XY plane. And we need to know when we cut up that cross section or cut up that volume into that 3-dimensional object into pieces, each cross section is going to be the same geometric shape. So every cross sectional cut will either be a square every time, or an equilateral triangle every time, or a rectangle every time. There is a video on GeoGebra. Actually, it's an interactive little thing that you can play with on GeoGebra that would be good for you to look at. It is hyperlinked on your weekly assignment page for day 4, and so you may want to go to that. So let's look at this example that's on your foldable. We have the base of a region. The base of a solid is the region bounded by y equals x and y equals x squared minus x. So you see your region here. This is very similar to maybe something that would be describing an area problem, but we're not doing an area problem. This is the flat bottom side of a 3-dimensional object. So just think of it sitting up from your desktop or from this image upward. And what we're going to do is slice that 3-dimensional object, and each slice in this case, in this first example, is going to be a square. So the basis of writing our formula using an integral, a definite integral, is going to be the area of a square. So first of all, we need to know our points of intersection for this region, this shaded region. This one is very obvious. It's 0, 0. This one's not quite as obvious, so maybe we need to do a little bit of algebra. Let's set the 2 equations equal to each other. Let's subtract x from both sides. Let's factor. And without continuing, I think you should see that the 0, 0 is one of the intersection points, and 2, 2 would be the other intersection point. So that's going to be important to us. Okay, the next piece is basically I want to represent one of these slices. So when I slice through this 3-dimensional object, I am going to actually slice perpendicular to the x-axis, and I am going to see a slice across like this. I'm going to darken it. Okay, it's going to go from here to here. So that is going to be a side of the square. I'm going to call it S as a side of the square. So we're going to get a side of our square, S, and each one of these little cross sections is going to be a square. Of course, we know that in a square, all the sides have equal length. So we have the other side is also S. This is like our little slice section right here. This is what this represents. When I do these problems, I always represent one of my slices, one sample slice in my shaded region so that I will have an understanding of what's going on. All right, let's go back up just a minute. So based on your Khan Academy videos yesterday, you know that what you're going to be integrating basically is the area of that cross-sectional cut. So this is area times thickness, because each one of these little slices is going to have thickness. In this case, this one has delta x thickness or dx thickness. So what we've got to do, our task to write this volume formula, is to represent the area of a square. So we should know that the area of a square is side squared. So that's going to be the basis here. Now, first of all, we need to know how long that slice is. Well, that slice length is basically the same thing you do when you find area. You need to do the top curve minus the bottom curve. The top curve is x minus, I'm going to be a good algebra student and remember to put my parentheses, and so it's x minus parenthesis x squared minus x. which we should realize is going to be 2x minus x squared. Okay, so that's the length of our slice, 2x minus x squared. So our area formula, and I'm going to write it as a function, our area should be the length of that slice, 2x minus x squared, squared. So once we have our area for our slice, our sample, then we can think about adding up all the slices that we would have, and that's going to be our integral. So our integral is going to go from 0 to 2 of our area formula, which is 2x minus x squared squared, and the thickness would be dx, so it's with respect to x. Now, I am not going to actually evaluate any of these definite integrals today because our task is to practice writing these new integrals for volume. I'm going to label this as volume. I can label it as v of x or v, and you should label your work as we're going so we can make sure that we can see what we're doing. All right, let's slide down, and now we have a cross section that's perpendicular to the x-axis that is a rectangle, and the height is 3 times the length of the base. All right, so let's represent that little base again. So there's our little base, S. Okay, but this time it's a rectangle, and it's 3 times higher than that. Now, I know this is not a very good drawing, but it'll do. So this is 3S. Okay, so there's our rectangle. So what is an area formula for this rectangle? Well, it's length times width, which is going to be S times 3S, which will now be 3S squared. Okay, now let's remember, what was S? Let's go back up and look. S is still the length of that slice, that simple slice in my shaded region. So it's still 2x minus x squared. So let's come down here and let's write that this is 2x minus x squared squared. Okay, so once we have our area, it's very simple to write your integral for your volume. So your volume will equal the integral from, which is still 0 to 2, and this is going to be 3 times 2x minus x squared squared dx. So the key is writing the area formula. Okay, so the first set of videos that you watched with Khan Academy were strictly rectangles and squares. The next set of videos that you're going to watch after viewing this and completing your 2 pages of your foldable are going to be on triangles and semicircles. So let's go to the next page of your foldable, and I've got to slide over here. Okay, all right. So now nothing has changed. We're still going to be doing an area of the cross section. Okay, that's still going to be the key here. The thickness is still going to be dx because we're going to work with perpendicular, slicing perpendicular to the x-axis. Although some of the Khan Academies might have done some perpendicular to the y-axis, I just want you to concentrate today on these pages where we're perpendicular to the x-axis. But this time we're going to look at triangles and semicircles. Now there are 3 kinds of triangles that you will typically see. You will see an isosceles right triangle with a leg in the base region, isosceles right triangle with a hypotenuse in the base region, and an equilateral triangle. So I think I've got an example of, 2 of the triangles, and then we'll do the semicircle. All right, nothing has changed. This is the same picture as the previous page. So this is still 0, 0, and 2, 2 as our intersection points of the 2 curves. I'm going to do the same thing I did before. I'm going to represent a sample slice here. So this is a slice. No change. My slice is still x minus x squared minus x, which is still 2x minus x squared. So that hasn't changed. But now we've got equilateral triangles. So let's think about an equilateral triangle. We know that all 3 sides have the same length. So if I represent, this is my slice, and it'll make me a little something that looks like an equilateral triangle, sort of, kind of. All right, so there we go, equilateral triangle. All sides are equal. all the angles are equal to 60 degrees. Now, on your reference sheet, you have a formula for an equilateral triangle's area. And that area formula is square root of 3 over 4 times side squared. That's going to make it very easy for us to write our A of X formula. That's the area of one of those slices. So that's going to be square root of 3 over 4. Remember, S is still 2x minus x squared. And that's going to be squared. Easy peasy. All we got to do now to get our volume is to integrate from 0 to 2 of square root of 3 over 4 times 2x minus x squared squared dx. Yes, the square root of 3 over 4 could be outside the integral because a constant multiple can freely move across the integral sign in multiplication. Okay, let's look at a slightly different one. This time our cross-section is perpendicular to the x-axis is an isosceles right triangle with the hypotenuse in the base region. All right, let's draw a picture of it. So here's my base region. All right, now this is going to be kind of weird looking at first. I'm going to draw a square. Okay? If I were to fold that square in half, I would have a right triangle with the leg in the base region. So that's why on your reference sheet, the formula for the area of a triangle that's an isosceles right triangle with a leg in the base region is 1/2 x squared. If I were to fold that in half again, I would have a right triangle with a hypotenuse as the base region. And so that's 1/4 of the area of a square. So that's why the area formula for this is 1/4 side squared. Now, you don't have to draw this every time, but that's basically what's happening. There's your little isosceles right triangle with the hypotenuse in the base region. So that means our area formula is quite simple. It's 1/4 that side, 2x minus x squared squared. And again, our volume will be very easy. It will be the integral from 0 to 2 of our area, which is 1/4 of 2x minus x squared squared, and our thickness are with respect to x. Okay, I think our last example is to look at a semicircle. Okay, so cross sections perpendicular to x-axis are semicircles with the diameter in the base region. So let's draw a picture. So there's our slice again. That's a little slice that comes out of the picture, and so we've got a little semicircle here. Now what we should realize is that the slice length is actually the diameter of the semicircle. The radius is 1/2 the diameter, which means it's going to be 1/2 of S. So we know that the area of a semicircle is 1/2 pi r squared. So it's going to be 1/2 pi times the radius, which is 1/2 of S squared. Now you can write it like that, or you can realize that, hey, if I square a half, I get a fourth, and if I multiply it by another half, and this is always going to happen with these problems, I'm going to get an eighth. So you could just learn that it's going to be 1/8 pi S squared. But if you want to develop it the way that I did every time, that's fine. Doesn't matter. What we do know is that our area formula is 1/8 pi S squared. S is still 2x minus x squared squared. Again, volume is now easy. 0 to 2, an integral, 1/8 pi times 2x minus x squared squared. Okay, that's where we're going to stop with your foldable today. You need to look at the Khan Academy videos. I think there are 2 videos and 1 practice set. You can also go to that GeoGebra site and play with that cross-section. It'll actually show you a visual of the 3-dimensional pieces there. And then tomorrow we will revisit some of these cross-sections and do a few practice problems.